Our airfoils are now ready to build wings and planes, so let's switch to the plane design module and let's define a new plane, which flow5 creates a default template for us, so we'll just have to edit the wing, Control W if you need a shortcut, select the Epler 174 which we loaded just for this reason, make it a 4 meter span sailplane, insert a midsection, move it slightly inwards, change its chords to 295 and 5 millimeters here, add some dihedral, why not, and add some washout or negative twist, I'm not sure of the word. Reduce the tipped chord to something reasonable so that we don't have Reynolds numbers of too small value. And finally change the paneling distribution, so let's switch to the top view, display the panels. I'll run with 19 panels in the chordwise direction using the recommended hyperbolic tangent distribution, which increases the density at the extremities but without creating panels of too small sizes. Flow5 also increases the density at the hinge, which is a good thing. Okay, in the span-wise direction, let's do the same thing. 13 on the inner surface, 17 on the outer surface. Prime numbers are beautiful and preferred. Use the hyperbolic tangent distribution, which densifies the number of panels at the locations of high pressure gradients, which would be the root and the tip, but also where the geometry changes. And that looks like a wing which we can use, so I'll save it. Same thing for the elevator. Control E is the shortcut. NACA 9 is the airfoil. Let's increase the density and leave everything unchanged. Perhaps increase slightly the span because we've increased the wingspan too, so that we get a reasonable tail volume. 0.39 should be good. And Control F for the fin. NACA 9, 11 and 11, and that's good. Okay. Now we have our three parts here. There's one thing which we must check at this stage, and that is the potential interaction of wake panels shed by the main wing with the downstream panels of the tail. If I switch to the side view by typing Y on the keyboard, in the real world you could imagine that the downwash induced by the main wing pushes the flow below the elevator. However, in the simplest form of potential method, such as the VLM or the panel methods in Flow5 and the linear polars at least, the wake is described by straight lines. In the case of the VLM, the trailing vortices extend in straight lines downstream along the X direction, and the wake panels extend also in flat panels in the X direction. And there is this potential intersection with the elevator. So let's have a look at it. Well, because I've added some dihedral, now the main wing intersects the elevator. This needs to be removed. This interference needs to be avoided. So we need to do something about it, even if it means changing the geometry to something which is not your real configuration. So in this case, what I'll do is I'll move the wing downwards by 30 millimeters and see what happens. Yep, it barely escapes. The wing panels, the wake panels shed by the main wing will barely pass underneath the elevator, but as soon as a flap is deflected upwards, for instance here on the main wing, there will be this intersection again. So I'll need to do something about it, and what I'll do is have a look at it sideways and move again the main wing downwards to -50. And this, I believe, should be good even with deflected flaps, but we'll check when we come to that. Well, this three-part configuration is ready to use, but to be complete, I'll add a fuselage, which I will bring in from the XFL type, the ones we have in XFL5, NURBS and quads. I'll use the NURBS type here. It will show up in a second. And let's see, well, it's been built seemingly in the right position. We have, it's almost tangent here. Now, know that for flow5 to work correctly, it needs to have a clear-cut intersection between the fuselage and the wing. A configuration such as this one, let's move it up, yep, that's fine. Let me move it up. Where there is only a partial intersection should be avoided. If this is the real configuration of your plane, well, do something about it. Either increase the height of the fuselage so that it intersects cleanly the wing, or move the wing downwards, still escaping the elevator panels. But try to avoid this configuration. One reason being that it will create warped strips in the chordwise direction, and flow5 calculates along strips which it expects to be more or less aligned in the X direction. Okay, so anyway, let's go back to -50. This is our valid configuration, and now we need to assemble those four parts into a plane. What is an assembly as far as flow5 is concerned? Well, it consists in building a fuselage mesh which will conform to the wing meshes. Right now, this is the XFLR5 configuration. The fuselage mesh does not conform to the wing mesh. Well, I'll save it, rename it to plane with a NURBS type fuselage. It's been built for thin surfaces, but it's non-conforming, and I'll use it later for comparison. Okay, let's duplicate this and build it to be conforming. Now, what do I mean by that? Well, let's demonstrate. We need to build the fuselage mesh so that it conforms to the wing mesh. We have two options to do this. We can build it for thin surfaces or thick surfaces. This refers to the type of modeling we will be using for the wings. In this case, you may see that the panels of the wings are located on the mid-camber line. This is a thin surface configuration, and the thick surface configuration would be one where the panels are located on the top and bottom surfaces of the wing. Up to version 752 of flow5, flow5 was closed source, so we could not link it to any other external GPL library. Now that flow5 is open source, we can, and it's now linked to libraries such as Xfoil and Gmesh. You can look up Gmesh. It's a powerful and versatile mesher which has open new options and possibilities for flow5, one of which is to build meshes for thin surfaces. So let me demonstrate. I'll switch to the assembly tab, build it for thin surfaces, select those wings which are connected to the fuselage, in this case all three of them, move to the fuselage mesh tab and define the parameters. Now, Gmesh uses many parameters to define its mesh. Three of them are exposed here. The minimum element size. This, as far as I understand, is a soft requirement for Gmesh. It's a hint only. Be careful not to run with too small values, because this would lead potentially to huge mesh sizes and to long meshing times, which you would have no mean to interrupt. So you would have to wait the mesher out or kill the app by interrupt the mesh by killing the app, which is very unfortunate. So be careful with this parameter here. 20 millimeters for a 1 meter and something long fuselage is fine. This second parameter, the max element size, I understand is a hard requirement for Gmesh, so I don't want any elements in this case longer than 6 centimeters. And lastly, this defines the number of elements in a circumference, so it tends to increase the density of panels where the curvature is high. Gmesh offers many algorithms. They recommend the mesh adapt as the most robust. The frontal Delaunay tends to build nice meshes, regular meshes. Okay, perhaps a bit too fine here, so I'll increase the mesh size, 25. Yep, that's good. All right, and let's have a look at what's happened where the two meshes connect. Well, you can guess that the mesh is conforming in the sense that the nodes of the panels on the fuselage are coinciding with the wing nodes, but unfortunately there were nodes that were created in between. These nodes are unfortunate, and in a previous video I explained that they should be moved to the wing nodes locations using the options available in the last tab. This would be better for the calculation of pressures on the fuselage, but it's also a bit on the perfectionist side because the calculation of pressures is very tricky and not precise on the fuselage at this location here. So there will be a workaround which I will explain when I explain plane calculations and the definition of an analysis. So we can live with this even if it's not ideal. To illustrate the conformance, I will hide the main wing, and you can, I believe, guess the shape of the mid-camber line here of the Epler 174, which is what we want. Let's have a look at the tail and see how it went. Let's hide the elevator. Same thing. We can guess the mid-camber line, which is a flat line, straight line, sorry, in the case of the Necker 9, so that's fine. And lastly, let's have a look at the fin. Well, the fin here, the mesh is not conforming. We can see that the fuselage nodes are not located at wing nodes. Why is that? Well, it's because the fin mid-camber line is located exactly on the split line of the fuselage, on its edge. If I activate the surfaces, well, you can guess the split line here. And this makes life very difficult for both the Open Cascade engine which flow5 uses and for Gmesh. So yep, there's not a good way out of it, but again, it's not critical. We can live with it. The calculation will still be sound, provided we activate some option in the analysis, which I will demonstrate later. And this plane is good to go, so I'll save it. And lastly, before I move on to calculations, I'll duplicate this plane and build it for fixed surfaces, and it will be conforming, so this should be the name. Alright, let's edit it. I'll leave everything unchanged except that I will assemble it for fixed surfaces and request a mesh from Gmesh. Let's hide the surfaces in this case and request a mesh and see how it goes. I'll hide all three wings. Well, we can see that Gmesh has built for us a fuselage mesh which conforms to the wing mesh, and we can imagine that the assembly of all four meshes, the fuselage mesh and the three wing meshes, will form a closed volume for us. However, I believe I omitted something which is very unfortunate. When we were in the assembly tab, there was a warning here, highlighted in red because I tend to forget all the time. And it tells us that the fin, which is a one-sided wing, is closed at its intersection. What does this mean? Well, let's open the fin editor, Control F. The intersection is here, and there are some panels which close the fin volume because this option here on the top right side is activated. If I deactivate it, it will remain opened, which is what we want because it's going to be connected to the fuselage. And this is something which is easily forgotten despite the red warning. In the case of a two-sided wing, Well, let's open the editor. Flow5 knows that each half wing closes the other, so to speak, to form one closed volume, so it defaults to deactivating the closed inner side option. And this time our mesh is ready for calculation, and we have our three meshes here. Before I demonstrate how to include the fuselage from a CAD file, I would just like to run a quick calculation to compare the conforming and non-conforming meshes. So what I'll do is I'll define an analysis, a very simple one, type 1, method, I selected thin surfaces, so I should select thin surface here. It's not, there's no check built in. Remove any flaps and remove any viscous drag and run the calculation. Or before I do that, I will define the same thing for the non-conforming mesh. Thin surfaces, inertia, flaps, no, okay, all good. Switch to the polar view, change the colors to differentiate the solutions. Color, green, and add some symbols in this case. Alright, and to save some time, I'll run a batch analysis, selecting the two polars I'm interested in, selecting the range we want, and running the computation. So we're running number 1. Okay, 1 down, 1 to go, and here we are. So we can close this and check our polars. So the non-conforming one is the green one. Well, I'll turn it to red in this case. I believe that, yep, it's the induced drag. We see a difference, not so much in the lift coefficient, but we have some difference between the behavior of the two. I believe also that it's mainly due because the fuselage mesh in the second case, in the non-conforming case, is pretty rough. So let's edit it, Control B, and let's increase the density to 31 in the axial direction, and let's say 13 in the hook direction. Let's save this. Don't need to assemble it because it's non-conforming. I will overwrite and run the calculation again, not storing the operating points. And I believe this will improve somewhat this situation. Yeah, it does improve. The calculation is almost the same. The results are almost the same. So in sort of a way, this vindicates the way we had been doing it in XFLR5, and which was bugging me all this time. I was wondering if the calculation was valid or how off it was from the one we would get with a conforming mesh. Well, the answer is here. And again, I'll demonstrate by activating an operating point, by creating an operating point for each. And yeah, let's do that. And what I will do is I will display the doublet densities here with the denoted by the Greek letter gamma. So these doublet densities, or these vortex circulations in the case of the VLM, are the elementary solution to Laplace equation. And it's from these doublet densities that all results are calculated. I'll come back to this subject in the video on plane calculations. We can see that in a conforming mesh we have a clear-cut separation of the doublet densities above the wing and below the wing, which is not the case with a non-conforming mesh. The doublet densities of those panels which I highlight here are an average of the values above and below the wing, which is unfortunate. It's an approximation. Again, I didn't know until we had this option to build a conforming mesh how good or how bad it was. Well, it's not so bad, but it's not ideal either. So the recommendation is really to do things correctly from the theoretical point of view and to use a conforming mesh. And lastly, what I would like to do is build a plane with a fuselage imported from a step file. To give you the whole picture, I've never had issues so far with Gmesh and the built-in type fuselage of the NURBS and quad types. I did have issues with the fuselage imported from a step file, as I will now show. So what I did is I went to the VSP airshow and explored for a sailplane fuselage. I found one built by author Marek Sell, the PW5. Marek Sell, I believe, is also the author of the nice P51 Mustang model, which you can find in the airshow. So I downloaded this sailplane and exported its fuselage to a step file, which I will now import into flow5. So I'll use any plane. They're all the same as far as the wings are concerned, so I'll duplicate one, and this one will have the PW5 fuselage, and we'll build it for fin or fixed surfaces, not sure yet. Let's edit it. Go to the Parts tab, remove the NURBS type fuselage and insert a fuselage from a CAD file this time. I'm in my VSP imports and I will select this PW5 fuselage. I tried several options when exporting from VSP. It didn't make a lot of difference in the end, unfortunately, so I'll use the default one. And it's been imported because it's listed here, but nothing shows up in the 3D view. Why is that? Well, we do have a warning here, which tells us that OpenCascade managed to import 16 faces, but didn't find or wasn't able to build a shell out of it. I believe it was the shell is not part of the step file. So we need to fix this. Let's edit the fuselage and we will fix the shapes. So the idea is to stitch the faces together, and this builds a shell for us, which means that our 16 faces are connected, and even better, they form a closed volume or a solid in OpenCascade terminology. Also, for some unknown reason, the shapes are imported inverted, so I will reverse them, and whilst we're at it, we might as well remove small edges and fix gaps, although I believe there aren't any in this case. Here is our fuselage, which I can now save, and it shows up in the 3D view. So let's move it in position 270 millimeters backwards and 30 millimeters upwards. Now we have a fuselage, but unfortunately it's not positioned well for our wing, so I'll move the wing forward, or rather no, I'll move it upwards so that we have an intersection at the trailing edge. So let's move this wing upwards. That's right. And we have this intersection, which I believe will be a problem when we assemble the plane for fin surfaces. And let's try it. Surfaces. Let's go with the mesh adapt, the most robust one. In the case of the CAT step fuselage, I believe we must target robustness. And there we are. Unfortunately, there was an error. Gmesh did not manage to build a mesh. Why is that? I'm not sure. There aren't any warnings or errors in the output. I did some trial and error research, and I believe it's linked to this intersection at the trailing edge. So what I'll do is in the parts tab, I'll move the wing forward by, let's say, 15 millimeters. So that would be 385. And try again. Same assembly, fin surfaces, run the mesh, perhaps smaller meshes, although that's not the issue. I'll run with 30 millimeters and 60 here. Make the mesh. And this time it went well. I can hide the wing, and there is our camber line. So ideally I would have liked for OpenCascade and Gmesh to be 100% robust and succeed in all cases. Unfortunately, this is not the case, and the errors I've had so far, I traced it down to intersections with the fuselage edges, or fuselage edges or split lines. And also we have some potential issues at the tail. So in this case, I think it went well. We have a conforming mesh. However, our elevator's mid-camber line was located very close to the stitch line of the fuselage. And we can see that this mid-camber line here created very small triangles or very stretched triangles. So Gmesh did a good job out of that, but unfortunately these are not very good triangles for the calculation. So it will still run, so I will keep them, but ideally you should try to avoid this kind of configuration. What happens if we request a thick assembly this time? Well, let's try it. Show the elevator and the main wing and run with the mesh and see what happens. Let's hide the wing, main wing. So things went well at the front. We have our conforming mesh, which is good. Let's see what went on at the tail. I think it didn't go so well. Yep. And in this case, I'm not sure why. Let's center the view on the tail. Neither the fin nor the elevator were cut clean open. What my trial and error so far seems to show is that it's linked either to this edge in the split line and the top one too here, or rather to the small cross section, because if I move these parts forward, let's say by 100 millimeters or 150 millimeters, 200 and 200, 1200 and 1200, and run the meshing operation again. Let's see what happens. Sorry. Well, yep, the meshing operation went much better. So, yeah, again, I'm not sure what happens because I'm not an expert by any means in these matters of CAD software and meshes, but my trial and error so far seems to show that the beam here has a too small cross section, and the edges of the CAD fuselage can be a potential problem, so you will have to work it out by trial and error. However, I selected this case also because I know it didn't work very well. In other cases, such as the P51 fuselage, which I imported from VSP, it went very smoothly, and it just went smoothly in most cases. This seems to be an extreme case for reasons that I am unable to explain. I'll save the plane, although I don't intend to use it anymore, but you never know. And I think that's about as far as I want to take it as far, on the matter of plane construction. So I'll end this video here, and next up I will demonstrate how to insert a plane from an STL file.